Tektite-R Electric Vehicle programming tutorial. First, go to our template repository, which you can find here. It'll also be in the video description. Now you can select code and you can hit download zip, which you can see will download a zip of their code. Now you go to your downloads, which will then give you this code. I'm just going to rename this folder to be the name of the repository. Open up STM32 Cube IDE and hit import. You'll probably see this. Go under general, go under existing projects into workspace. Now find your directory. Make sure to select the project. It should list Tektite-R EV template and hit finish. Now you will have the template folder down here. So you can go into core, source, and then open up control.c. This is the most important file. You need to go under the go function, and this code specifically is what will control your vehicle. Now, you'll see that I've already written out instructions for how to code specifically, and also I've written out like an outline for a trapezoidal motion profile. So you'll notice there's an acceleration phase, a full speed phase, and a deceleration phase before it finally stops. I'll go over what specifically to put in this later, but now let's see how to program this. First, while you've opened up this control.c file, over here you'll see a hammer button. Press that and that'll build it. So you'll see some compiling, and you should hopefully see no errors here if you've programmed everything correctly. Now that you've done that, open up STM32 Cube Programmer. Okay, so now we're in STM32 Cube Programmer. Press open file. Go into your downloads, go into here, your folder, go into debug, and find something that says Tektite-R EV template.elf. Make sure it ends in ELF. Press open, and now you've opened up the code. Now we're going to flash this to the board. Alright, so now we have our vehicle, the code open in STM32 Cube Programmer, and this USB cable. So first, we can see that we have the normal code installed on the device. Now we're gonna flash the code, and note that this code is just a template code, so it shouldn't do anything. So turn it off. You'll see there are two buttons on the board. This is the reset button and this is the boot button. Hold this button and plug in USB-C. Now you can let go. You'll notice that none of the lights turn on anymore, and that's because we're in programming mode now. So go under here, switch from UART to USB, refresh this, and you should see that USB 1 shows up. Press connect. So you'll see that now we're connected, and you'll notice that we can actually go to device memory and look at the code that's on the vehicle. But now we're going to go to our code that we just compiled, and for me, I haven't actually programmed anything, so this shouldn't do anything. And just press download. You'll see it's doing something. It's rewriting it. You'll get this notification, and you'll see that now we've successfully downloaded it. So now we've downloaded the code on the vehicle. Let's see what happens. Yep, you can see the green light turns on, but it doesn't do anything afterwards. When I press red, it stops, which is nice. Now let's talk more about how to actually program this. Alright, so now let's talk about how you can control the motion of the vehicle. So first of all, note that there's two things in this board. There's the actual CPU over here, which you can control, and there's the ESC, right? And the ESC is what is directly connected to the motor. So the way that you communicate with the ESC is over this connector right here. So this has a white, red, and black wire. Red and black are power, and white is a signal wire. So what's happening on the signal wire is the chip on the board is sending a PWM signal to the ESC. So what's a PWM signal? Well, basically, let's say that you have a signal, right? So this is time, and this would be voltage, right? And statistics don't matter, but essentially what happens is that it turns on for a short amount of time before turning off. Then it keeps on going, turns on again, and this is constantly repeating, okay? So this happens at 50 hertz. So what that means is that this right here, this total amount of time before it repeats is 20 milliseconds. And what you control is the width of this. And generally, with this ESC, I found that 1100 to 1900 microseconds, or 1.1 to 1.9 milliseconds, is what the ESC likes to see. So this 1.1 will be braking. This 1.9 will be full speed. And you kind of want to be in the middle, like 1.5, no speed, like zero speed. So what we want to do is we want to create a trapezoidal motion profile, right? So we want like velocity, which is funnily enough just lowercase of voltage, versus time. And we want our graph to look like a trapezoid. So we want to have constant acceleration and constant deceleration. So to achieve this, first let's start off with the deceleration because that's simple. So let's look at what we're commanding to the motors. So we're going to be graphing this PWM signal versus distance, because we really want the motion of our vehicle to be in terms of distance rather than time, since we're trying to go a specific distance rather than execute anything over a specific amount of time. Which is unlike robot tour, for example, where you do have to have your motions in terms of time in addition to distance. First, let's look at our PWM versus time graph. And what's going to happen is that this should be pretty much constant on the way up, or it should be diagonal on the way up, because the PWM signal controls the velocity of the motor. Now we're going to reach a full speed section, at which point it's going to be horizontal. And then what's going to happen is that we want to slow down. And instead of actually putting like a downward signal, I just have it like instantly drop off before we kind of reach the end, at which point it drops to negative, right? Let's say that this is like 1.9, this is 1.5, 0 speed, and this is 1.1 ms, right? So we want to achieve this, and what will happen, our velocity, since we have the inertia of the moving vehicle, it'll slow down during this period instead of just instantly stopping like the PWM signal. So because of this, let's look at our PWM versus distance instead. Right. So we're going to have our full speed section, right? This is going to be 1.9 milliseconds. Now this, we're going to have this obviously similar to this because, and now we actually know the quantities for this. So we know that the distance from here to there, right, is decel underscore dist. And this is a variable that you can access in your code. And basically, like, let's say this is by default 1.5 meters, but you can change this through the serial monitor interface that we've covered in the run tutorial. And let's say when this is 1.5 meters, that means that when you're 1.5 meters away from the ending, right? So this right here is the total distance. And when you're 1.5 meters away from the end, you want to drop your PWM down from 1.9 to 1.6, which is the minimum speed you need to still keep on moving. Okay? And then finally, when you actually reach the final distance, you drop it down to 1.1, which causes the motor to brake and you stop. Now let's talk about this acceleration phase. And this part's interesting because we want it to be a straight line in the PWM versus time graph. However, this is a PWM versus distance graph. So interestingly, this should actually be a square root. So this should be square root of distance up until you reach the full speed at 1.9. So this should start off at 1.5, and you should Use square root of x to interpolate from here to there until you reach 1.9, at which point you can continue at full speed, reduce it down to 1.6, reduce it down to 1.1. And also note that this part where we are accelerating with square root of x, this distance should be accel underscore dist. And this is just another variable available to you that will be customizable by you over the serial terminal. Now let's talk about the math of why it should actually be square root. And this is completely optional and you can stop the video right now. But if you're curious, this is a really cool application of like the calculus that I learned last year, for example. Let's say we're using square root, right? So we can use dx dt, right? So this is just velocity. And we say this is equal to square root of x. Now, you can reorganize this such that you basically have 1 over root x dx equals dt. When you reorganize this, you get 1 over square root x dx equals dt. Now you can rewrite this as the integral of x to the negative 1/2 dx equals integral of dt, integral of, let's say, 1 dt. Right, so when you integrate these, you get 2 root x equals t plus c. We want x to be proportional to time, so we can just get rid of this plus c since we only care about proportionality. Now, if we change this, we get x equals t squared over 4. At this point, you can differentiate this, or you can plug this into this original equation. You'll get the same answer both ways, which is dx dt equals square root, for example, I'm just going to plug it in the original equation, t squared over 4. So now we know that velocity is equal to t over 2, which shows us that if you use this square root of x curve, you actually get that dx dt is proportional to t.